This is Sarah Wilkinson from Humber College and the University of Guelph-Humber. In this next video in the nervous system series, I'm going to discuss how neurons communicate, or neuron and tissue communicate, at the synapse. In previous videos, I've covered the electrochemical gradient, the divisions of the nervous system, neuron anatomy, and action potentials. I would encourage you to watch all of these before carrying on to this video about the synapse. In previous videos, I discussed neuron anatomy. Specifically, we talked about how an axon of one neuron becomes axon terminals and communicates at the dendrite of the postsynaptic neuron. So action potentials travel down one axon, and those signals need to be sent to another neuron or tissue. That's going to occur at the synapse. So as you can recall, we've got the presynaptic neuron and the postsynaptic neuron. And contained within the presynaptic neuron are synaptic vesicles with neurotransmitters within them. For simplification purposes, I'm going to make the plasma membranes into lines. So here we've got our presynaptic neuron, our postsynaptic neuron. We've got synaptic vesicles with neurotransmitters within them. And on the postsynaptic neuron, I have receptors. So here are some receptors for neurotransmitters. So let's label that. Presynaptic neuron, postsynaptic neuron, and the space between the two neurons we call the synaptic cleft. One thing I haven't discussed yet is the concentration of calcium ions. Calcium is found in higher concentration outside the neuron in the extracellular fluid versus inside the neuron. In axon terminals, we have calcium channels. These calcium channels are voltage-gated channels, meaning that a change in the voltage within the membrane will cause them to open. As you know, arrival of sodium ions, otherwise known as a wave of depolarization, will cause these voltage-gated calcium channels to open up. When they open up, calcium can move down its concentration gradient into the neuron. This movement of calcium ions causes the synaptic vesicles to move towards the plasma membrane. When the synaptic vesicles fuse with the plasma membrane, neurotransmitters are released into the synaptic cleft through excitatory. Once in the synaptic cleft, the neurotransmitters can bind to receptors on the postsynaptic neuron. Depending on what neurotransmitter we're talking about, different things will occur. However, for the most part, neurotransmitters will cause opening of chemically gated channels. These channels might be sodium, potassium, or chloride. And depending on what channels open up, will result in either an inhibitory effects or excitatory effects. So let's look at this a little bit closer. There are some neurotransmitters that are inhibitory, while others are excitatory. Inhibitory neurotransmitters cause hyperpolarization by stimulating potassium channels to open up. So if a potassium channel opens up on the postsynaptic neuron, potassium will leave the neuron, rendering the inside of the neuron hyperpolarized, or more negative. This will make it harder for that neuron to reach threshold. Remember, threshold being the membrane potential around -55, after which depolarization will definitely occur. Conversely, excitatory neurotransmitters cause graded potentials. Most excitatory neurotransmitters cause sodium channels to open up. This will result in sodium entering the neuron and bringing the neuron closer to threshold. If enough excitatory neurotransmitters bind to receptors, threshold is likely to occur. Once the neurotransmitters have exerted their action, either by opening potassium or sodium channels or chloride channels, one of two things can happen to them. Enzymes might degrade them so that there's no neurotransmitters left in the synapse. The other option is that some neurotransmitters are taken back up into the presynaptic neuron. It depends what neurotransmitter we're talking about. So let's review what happens. At the axon terminals, an action potential will arrive, so a wave of depolarization. This causes voltage-gated calcium channels to open up. Calcium will then move into the neuron, and this will stimulate synaptic vessels containing neurotransmitters to move to the plasma membrane. Through exocytosis, neurotransmitters will be released into the synaptic cleft, where they can bind to receptors on the postsynaptic membrane. Binding of neurotransmitters can cause chemically gated channels to open up, and depending if the neurotransmitters are inhibitory or excitatory will depend what ion channels open. When the neurotransmitters have exerted their effect, they will either be broken down by enzymes or taken back up into the presynaptic neuron. I hope these videos have been helpful in you understanding how the nervous system sends action potentials. What I haven't covered is how a neuron communicates with the tissue. For example, a motor neuron affecting skeletal muscle. I hope to cover this in future videos.